better? Can you hear me? Cool. Awesome. Okay. Maybe. All right. So welcome everyone. I'm gonna try to follow the previous presentation, which was pretty awesome. So I'll try to give something good too. Okay, so I'm going to talk about how we ended up using Redux in our SDK to implement a new UI that we changed to. So this is pretty much a story of how we moved from an old kind of classical implementation of an architecture of an app to the new and fancy unidirectional dataflow architectures. Something kind of a Redux on Elm, and how it was the path and what did we learn from it. So my name is Omar, and I'm a senior engineer here at Zendesk. That's my Twitter account if you want to follow me. I work on the iOS and Android SDKs for Zendesk. I also organize the Swift meetup, which we abandoned six months, but it's going to happen, and the Elixir meetup. So both of them are hosted here, so you can also join us in the Elixir or Swift meetup once we put them on meetup.com. So we moved up from changing the SDK to, so that should have been a GIF or a GIF with stuff moving, but. So okay, so this should have been moving, like the mouse should have clicked on contact us and stuff should have appeared, but it's not going to happen. So what I was trying to explain here is we moved from kind of a model interaction of an SDK where you popped up your screen, you typed up some text, and then you attached images, and then you pressed on done, and we would package all your interactions and your text and images and send them as one request to the server. And that was our previous SDK. So we were moving toward yet another non-moving GIF here, which was our new UI, which is more of a chat or conversation UI. You can write your messages, and then you can wait from messages from MQTT or socket connections, and then it's an active, interactive kind of interaction. But since the GIFs are not moving, I don't know how. All right. So historically, I'm sorry, but something should have happened here, and it's not happening. So I'm going to move to the next slide. So historically, we had the MVC pattern. Do you know what does anybody know what the MVC pattern is, or did you work with the MVC pattern? Like a raise of hand. All right. So the MVC pattern is one of these very, very old patterns. Could have been created in the 90s. And it splits your application to a controller, a view, and a model. The controller would update, would pull stuff from the model, and it would put them inside a view. And then actions would happen on the view, which will then be moved to the controller, which will then update the model. So for our old implementation of application, which looked like this, where you type some text and then you attach images and then you press on send, it kind of made sense. The application was not very interactive. Most of the views were passive. Not a lot was happening on the screen. It was a very passive screen, and it was like it's a model interaction where you just write stuff and it goes to the server, and then we wait for a request, and when we get back a response, we finish the screen and the whole interaction. And we moved toward a more interactive kind of interface where you write a message, and the new messages appear from the server based on MQTT or socket events. So we thought about if MVC would be the architecture that we want to use for this new interaction, which would serve us for the next 2 or more years. When we thought about this, we thought that maybe we have too many different elements and UI components in the screen. So we have multiple conversation, which means that we will have multiple flows of chats. We might have multiple events coming from REST API, MQTT, local changes to the storage on the disk. So user interactions that are coming from either where you tap the attachments, you write text. So when we thought about if MVC would be our solution, we gave it a first cut, and we ended up having something like this. We ended up having view controllers that are huge, that deal with lots of models and lots of views. The controller then has to deal with network and other view controllers or other controllers and databases. And this is one of the problems that led some people to call the MVC pattern as instead of model view controller to be the massive view controller. This is like where it's ended up. So you end up having these very, very large model view controller. So we thought about what other architectures are there. So when we thought about these architectures, we put some constraints on what a good architecture that would serve us. So we want an architecture that would ensure that the UI is correct. By correct here, I mean whenever you create a view and you put some state into it, the view should be correct. So we should be able to say this view is correct now, and I should be able to put another state on the view, and I should say now it's correct. So it's not possible to have a view that is not correct, like that has a strange color or elements are out of place or behaving incorrectly. We have to be able to implement and build consistent UI. So what is a consistent UI? So if I'm on the screen and I receive a new message from wherever, could be from MQTT or could be from sockets, the message should appear on the left hand, on the right pane. So I should see the new message there, but also I should see an update on the left side. So that means that there should be some way of notifying both the views, and more importantly, I should be able to say when something changes in my application, I should be able to say, yes, I can assure that this view and this screen is consistent. There's no way of, for example, receiving a message and appearing it, and for it only to appear on one side and this side not being updated. This is sort of one of the problems that also led to one of the architecture we used eventually from Facebook. When I reach that, I'll explain more about it. We want also to be able to create or have an architecture that is easy to structure. It will be easy to know where we put the code, where we put, for example, logic, where is the network, all these kind of things. It would be nice to have an architecture that would help us divide the concerns that we have in our windows or in our screens. In the MVC patterns and other derivatives like MVVM or MVP, some elements of the architecture end up being huge, like the view controller in MVC and the view model in MVVM. And since they are like this place where you just drop code, they just grow and grow and grow. And we wanted an architecture that makes it not impossible, but very difficult. And lastly, we think that for us, these three elements together would lead to improved developer happiness and performance. So when we reviewed a couple of architectures, we found that the one that suit us the best are the unidirectional dataflow architectures, or for short, they are called Unidir or unidirectional architectures. Two very popular architectures that are there are Flux and Redux. Flux is the original unidirectional architecture, which describes how the data works. So these architectures, they will describe how the data and the actions flow while you are interacting on your screen. Redux is, I think, who is familiar with Redux and Flux? Raise of hands. Right, a couple of people. Redux is an architecture that was inspired by the Elm programming language, which is a relatively new programming language that build your application in a way that the data flow and the actions flow easily. So these are the very, very high level view on how these two architectures behave. Actions always flow down the stream. So if you have an action in Flux, it goes to the dispatcher, which we're not going to talk about each component. We will expand on them next. So the actions always flow downward, and sorry, actions always flow to the dispatcher, and then state always flows downward. So state is downward, and actions is upward. Redux is very similar. There was the difference here is that instead of having a dispatcher, you have a reducer and state and selectors, which helped making Redux a more implementable architecture. Flux was more of like a blueprint architecture that was not had multiple implementation. Redux is kind of one of them, but not really. So once we reviewed both of these, we selected the components that would make sense for us. And we ended up with an architecture that looks like this. So we have, all right, so we have views which would represent just any view on the screen, actions which represent any action that you could take. For example, you can tap on a button, or you can drag stuff around. All these would emit actions. On the left side here, we can see that other action could enter. This could be network actions or system actions. These are actions or other UI actions. They all end up being in one reducer, which takes these actions and produce a new state. All right, so as we go through an example, let's remember what were our constraints. So we wanted this architecture to provide correctness, consistency, structure, and developer performance. So for this architecture, let's start with the view and state and see how they map to our screen or how they map to our application. So let's remember our example that we had. So we had this chat interface where we have conversations and we have messages for one conversation. We can tell by this UI that probably we selected the first one on the top, and that's why we have this conversation for it. On the left, we can see that we have these 3 conversation items. These are the views. So one conversation item view is one of these items that has a user avatar, a text, a subtitle, and the date. So each one of these is one of these type of views. On the right, we have the message item view, which represents a message bubble, which has the text, and it could be either left or right. So the left and the right bubbles are of the same type, which is a message item view for this example. And we have a message list view, which represents one flow of messages. So for this example, it's the view on the right that has 2 messages inside it. So let's zoom in on the message list. So this view, which represents the message list, it would have this kind of state. So for the message, it would have a message state that, for the purpose of this talk, I'm gonna use Swift here. So what I'm saying here, I'm defining a structure which is like a value type, which is like a data structure, a value type that contains 3 elements. In this example here, or in this specific state, I have the content, is agent, and is delivered. The content represents the content that ends up being in the bubble. The is agent represents whether it's on the left or on the right, and is delivered, if it's set to true, we get is delivered label, which is just down under the first cell. Also, the message list itself has a state, and its state is represented by an array of messages, which each element of this array is also a message state there, and last delivered index, which for our example is an integer, and it would be 0 or 1 if we start from 1. All right. So if we create one of these message state and we give it the content, hey, I'm having an issue with, and we say that the agent is false and is delivered, and we create a message item view, we end up with that cell on the one on the top, which is since is agent false, that would be a user cell. So it's a cell that you actually sent. So it's your message. While if we use the same data structure and we set true, so now it's an agent message, and we also feed it to one of these views, we get the other one. All right. So for the table list, if we create two messages, a message for the that is not agent and one that is agent, and we create a message list state. So it's a list that has two messages, and the deliver index is one. Well, really it should be 0 in this example, but it's a typo. It should be like delivered index is 0. If we create this kind of state and we feed it to this time it's going to be the message list view, so the whole view that represents the message, we end up with the whole view. So we end up with a view that has two different cells. One of them is two different items. Sorry, one of them is a user one, and one of them is an agent one. So by having this kind of architecture where we create a state, and the state is a data structure which doesn't have, it's only like data, doesn't have code, only data, no behavior, and we set it to this message list view, we think, and we would try to prove that it represents correctness. So we can only have a correct UI. So and we enforce it by how? So when we create one of these data structure and we set it to the view, whenever we set a new state to a view, we end up with one new view. So we end up with a view that is only on the left and it's gray, or one that is on the right and it's white. So since setting a new state to a view would generate, setting a new state to a new view, we would generate a view that has that shape. And also, since the state here is immutable, in this data structure here, I'm using lets, and lets in Swift, when used, means that this is immutable. So I couldn't, if I have an access to one of these items, views, and I say, I want to change the state on this, I can't. The only way of updating the state is if I generate a new state and set it as a property on one of these views. So by having these two elements, I can easily enforce correctness. Since I cannot modify the state of a view except by setting it, then I can ensure that this view is correct at all time. Also, I can test for it. So how can I test for a view that is correct? So I could take this kind of, if I create this kind of state where with this string and is false and is delivered, and I feed it to one of these item views, I will always get one of these views. I can then compare it with a store view. I can snapshot a view, and then I compare it with this newly generated view, and if they match like pixel-wise, I can say that this view match 100%. Once we move to this new architecture, we actually removed all our UI tests that would actually spawn a new emulator or simulator and then do stuff with it and check that the label is there. What we did is we now create these views, we set the state to them, and then we compare them with an earlier snapshot. That means that we can, instead of UI test, like instead of doing a behavioral test, we can just go and do unit test even for views. But how can we enforce consistency? All right. So in this example here, I'm creating a message list state, and I'm setting it to the message list view. And both these values of messages and last delivered index is what makes this final view. So the last delivered index would decide which one of these two messages is delivered. So that means there's the parent. So we have this kind of parent-child relationship where the parent is this list item, list view, and the children are these list items. And since I can only set the state on the bigger parent, which will then distribute it to the children, I can enforce that there's no way of having two delivered items. I can only have one delivered item because in my state, I define the delivered item as a property of the bigger container view. And since the state is we are using lets here, since they are immutable, I cannot go and take a grab of one of these states and just change the last delivered item or just feed a new message to it. I can only create a new state with the new messages and then feed it to the view, which would generate a whole new view. So we finished, we talked about the view and the state. Now for the action. So for this UI here, what action would I have? Whenever I select one of these conversations on the left, I would get a selecting item action, which looks like this. So it's just a stage, it's just data, just a new data structure that has what is the conversation index that I selected. So this is again only having data and no behavior. If I write a message and then I press on send, I also get a sending a message state or action, which is another structure that has only the content. So it's just a data structure. Whenever I do this action, I generate a data structure, which then I'll see how I'm going to use it. But for now, what happens is I just generate one of these data structures. If I send an API to, if I send a REST API request and I get a success, I also get one of these message delivered actions, which will have what is the index of the message that was delivered. And if I get a socket on MQTT request for some feedback that the server would push to me, I would get a new agent message received action, which have the content and the agent name. The agent name, we're not really using it in this example, but we could use it in the future. So, from this slide, we can just see how actions are also only state. So, sorry, actions are only data structures. They're only data. So that means that we need to consume it somehow. So how do we consume it? We consume it in the reducer. So the reducer bit here is a function, or you can think about it as a pure function. So it doesn't have any state. It takes in an action, which is one of the actions we saw before, and it takes the current state of your whole screen. So for the screen, that would be the state of the conversation plus the state of which item was selected. And then it generates, depending on some logic inside it, it generates a new state, which is then get fed to the view and generates a whole new view. So for these, let's consider how these three items would change, these three actions would change the state in the reducer. So if I get one message submitted action and I get a message list, I should get a new message list. So if my message list contains 2 messages and I get a new message has been submitted, I should create in the reducer, I should create a new message state with that message content, and then I just return a new state that contains the original 2 plus this one. This new state is getting fed to the UI, which would change the whole UI. So it's a full redraw of the UI. Similarly, if I get a message received, so this is when I receive a message from MQTT. So I'm getting just what the MQTT service would generate one of these actions and when send it to the reducer. So for this message, I will create a new message state and then return a state that contains both of these 2. And then if I get one message that was sent and it was received by the server, I get the message delivered, which would only change the message last index here, which will, when it's set the UI, will change the whole UI based on this index value. So the reducer would be just a glorified pure function that takes an action and state and generate a new state. And we will have some kind of switch here where we switch based on which action and then we produce a new state based on that. So we talked about how correctness and consistency worked before. Let's see how this architecture would define structure. So we only have these 4 components in our architecture. We know that actions only, they only talk about how the state can change, so they only trigger the state change. The reducer has some logic that takes an action and based on its logic would generate a new state that is a modified version of the old state. The state is a state that represents what state your view and its hierarchy is in, and the view is a UI element that just knows how to redraw itself. So, so that would define structure, but what about developer performance? So we think that by having, we thought that by having correct UI, which means a UI you cannot break easily, and consistent UI, you cannot have 2 messages delivered or some two things that two different views that are not consistent together. You have reproducible and deterministic UI. That means that whenever you generate a new state, depending on this state, you get a new view, and it's deterministic. You can just, wherever you want to generate a specific permutation of a view, you just create this state and set it to a view. You get reactivity and to internal and external events. So the events can either be from views or can be from MQTT or from sockets or from wherever. We can have reusable state and reusability of the state and reducer. So one thing we did is we ported an application from iPhone to tablet, to iPad and Apple Watch and Apple TV, and we were able to use the state and the reducer since it wouldn't contain anything that is responsible about is concerned with UI views from iOS. So that worked pretty well. You have strong code separation, and you have unit testable UIs by doing this kind of snapshot UIs, and that's how you get a happy developer, I hope. I guess a happy developer would also be a performant developer, maybe. And that's it for me. Question? Questions?
Did you guys try any other architectures apart from MVVM or Viper?
All right. So the question is, did we try other architectures like MVVM or Viper? So when I said MVC, we really were MVVM, but since iOS forces you to this pattern of MVC with the view controller main component of your screen, so you cannot really go pure MVVM. You can go MVVM plus a C somewhere in that acronym. So MVVM, we tried it, but we ended up having bloats everywhere. For Viper, we thought that, so we like from Swift its immutability and its functional paradigms, and like you can have pure functions, you can have like high order functions. So we didn't want to go to an architecture that looks lots like Java. It was like Viper was created by, it's a permutation of clean architecture which was created by Bob Martin for Java. So it has lots of, like, you need five different classes, and then you have Viper, you have another one. So we didn't want to end up with an architecture that is very transformational and it's very opinionated. While this looks very complicated, I'm going to skip a couple of slides. Animations. Maybe I can just, So the whole architecture for us, for implementing this is not, all right, this is the next slide. I think this is the next one. All right, so the whole thing, this is the whole architecture. That's our whole architecture. It's like 60 lines of code, but it's more of a way of thinking of how you build your UI and how you build your application. So we wanted to go with something that is not transformational and not super obtrusive to, so Viper would look like too much to us. Yeah, go ahead.
Sure, your example, that has to be synchronous, correct? Like a company synchronous thread to access reducible first. So how do you prevent that from being a bottleneck for your UI?
All right, so the question is, the reducer is only synchronous, so how do we do network calls and access databases or stuff like that? So one bit that I left out from this is the middleware. So we have in Redux, and also we are thinking about this idea of middlewares. So we would put some bit that acts, that captures events or actions before they go to reducers. And they could emit an action to reducer. For example, let's think about you are creating a new message and you want to send to a server. It would capture the event and emit, like, draw this new item, and then at the same time it would dispatch a call, but it's not in the reducer. It's before the reducer. It's like a middleware. If you think about like Node.js or something like that, there's this middleware architecture.
Before you get the reducer.
Like more of a dispatching, not really queuing, but just dispatching you. But yes, like.
Hi, have you heard about chatbots from Facebook? They have something very similar. It's just, I was wondering if they are doing, like, I'm using that chatbot in the company, so we use that one as a training, so you can, like, message. So it's the same structure in that kind of way, like, because what I'm seeing now, like, that you can implement in an application or in a web service, something like that.
Right.
Yeah, it's kind of similar as well.
Yep. So the question is if we did use chatbox or thought about it. So what we're building here is actually an SDK for Zendesk. So we couldn't really use something from Facebook because it's not made by Zendesk. But the architecture, yeah. Yeah, the Flux and Redux are all like children of Facebook. I don't know Chatbox. I'm pretty sure they're using some kind of this architecture because they own Redux and they own React and everything. So we are heavily inspired by work that Facebook did, for sure. Go ahead.
When you start to implement Redux and you have a few actions, it's easy to understand you have the map of the flow of the action is easy to remember. Do you have any tool to map when the actions number grows and how is the flow and even, I don't know, part that you are not working today to remember how is the flow? Are you mapping or doing something like that?
Right. So the question is, what do you do when you have lots of actions? How do you keep track of flow? To be honest, we are hitting some kind of not limitation. Like we don't know how much will this scale. But like for example, the question of middleware and how do you patch stuff on the network, we didn't know about it when we started. We knew that React has or Redux has the middleware, but we thought that we could not use it, or we just like hack it around. So tooling wise and debugging wise, we don't have the answer at the moment. But I don't know. I don't know how to answer. So I guess that we don't know. But
it's one of the biggest problems.
Yeah.
Grows a lot of actions.
Yes.
Remember, even today, or
yes.
Someone joins the team, how do we explain the flow?
Yep.
Not tracking the code.
Yep. So one of the things that maybe is a bit more helpful with our architecture is it's built on Swift. So there is some static typing. So preserving all the static typing of the language and for the actions and reducers was one of the goals that we aimed for. This talk has been taken from a more Swift-oriented talk, so that bits are not there. But maybe with having some typing information, you can get more context of what you did and what you didn't. But we're facing issues where like we didn't handle this action, what happened with this action, and it just goes to a black hole. So yeah, we didn't hit that. Dale?
You emit an event only when you hit submit, or for every card you use?
So both of them. So at every character we type, we emit an event, and then when you enter the focus and when you leave. But so this architecture doesn't really enforce the way you're handling your UI. Is not really a React, doesn't really force you to write in a reactive pattern. It's more of how to organize your code. But internally, for example, our UI internally is still very like much plain old Swift code. Nothing like RX or any other kind of. Yeah.
How do you handle the animation codes and navigation as well? For Java
All right. So for navigation, we have kind of a router implementation where we will receive the actions, and based on that, we would route and handle it using the segues. It's not perfect. But we are prototyping other kinds of ideas. But for now, we are aiming toward the routers. For animations, as I said before, it's like mostly plain old Swift code, so it would be just in a view. And this is another like problem where JavaScript might have the edge on these kind of platform or architecture because they can just like make things happen in objects, while in iOS you cannot really have new stuff happening. All right, thank you.
Thanks, Mariano.